So I'll talk today about perception, illusion, and truth. And I'll begin with a demonstration. I'm showing you an image, a blank screen, and an image. Do you notice anything different between that image and that image? If you see it, don't let it out. How many see a difference? Does anybody see a difference? 1, 2. How many do not see a difference? Okay. Keep looking. Well, can you see the difference there? Okay. Now you might wonder, how in the world did you miss that? Right? It's huge. It's in the middle of the screen. It's sort of important. You don't want to leave without it. and yet we didn't see it. For most people, this is quite a surprise. We have beliefs about our conscious experiences that are deeply false. And experiments can actually reveal a lot about consciousness and our conscious experiences that we didn't expect to be true. I'll give you another chance. Again, don't blurt it out if you know it. Anybody see the difference yet? How many do not see the difference? Okay, notice that you're searching. It looks like it's the same image both times. You can't figure out what's going on there. And then all of a sudden when you see it, you can't help but see it. So there's a bar going up and down here, right in the middle of the screen. Again, this is not some tiny little thing tucked away. So your conscious experience, we all think that we have a detailed experience of the world around us. And that's an illusion. You have high resolution vision in a disk about a radius of your thumb's width at arm's length. That's all that you see in high resolution. And as you move your eyes around, you're moving that disk around, but we have the illusion that we're seeing the whole world in high resolution. It's very easy to assume we know more about consciousness than we really know. The field of psychophysics that I work in, we study conscious experiences for many, many decades now. We've done that, and it's full of surprises. You can learn a lot about your conscious experiences that you didn't know. You can sort of see what I was talking about. If you look at the center dot there, you'll notice that all of the letters at each concentric circle are about the same visibility. And that's because the resolution of your conscious experience is dropping off that fast. There are tight correlations between brain activity and conscious experiences. There's an area in your brain called area V4, which is shown there on the left, and also area V4 alpha, shown here, that is highly correlated with your experiences of color. If we take a magnet, a transcranial magnetic stimulator, and we touch it just outside, on your skull, outside here, close to area V4 and inhibit, you will lose all color experience in your left visual world. So you'll see normal color in the right visual world and just shades of gray in the left side of the visual world. You turn the magnet off and you'll experience the colors come swishing back in. So we can play with your color experiences. We know that there are tight correlations between neural activity and conscious experiences. In fact, we have dozens, perhaps hundreds of them. I'm just giving you one. We have hundreds of correlations like this. So what we're very interested in cognitive neuroscience is to understand not just the correlations, that's the data. So the correlations are abundant. We want to understand in principle what is the relationship between brain activity and conscious experiences. And this is called the hard problem of consciousness. We have hundreds of correlations between brain activity and conscious experiences, and my colleagues have been for the last 4 decades intensively, but for the last 3 centuries, thinking about the problem, how could brain activity cause conscious experiences? How does neural activity in the brain cause conscious experiences? That's the assumption. And as we'll see, there's not been any progress on that problem. It's a physicalist approach. The assumption is that brain activity is fundamental. Brains exist even when they're not perceived. They have causal powers, neurons have causal powers, and somehow the activity of neural activity causes our conscious experiences. That's the physicalist assumption. And I would say 99.99% of my colleagues are making that assumption in their work. Somehow neural activity causes our conscious experiences. And what's happened is we've made no progress. We have no idea how neural activity could cause conscious experiences. All of the theories that have been proposed so far are only believed by the graduate students of the person who proposes them. And in every case, right at the point where the neural activity gives rise to the conscious experience, a miracle occurs. Consciousness, like a rabbit, pops out of the hat. And I'll be very, very precise. There is no theory that can explain how a specific conscious experience, like say the taste of chocolate or the smell of garlic or whatever, can arise from a specific kind of brain activity. No one has been able to say this brain activity will necessarily cause the taste of chocolate. It could not cause the taste of vanilla or the smell of garlic. There's nothing on the table, nothing. So they're not even wrong. There's nothing to even say it's wrong yet. So I'm going to make a proposal today and motivate it to suggest that maybe we need to go the other way. Instead of starting with physicalism and neural activity, that we need to start, as scientists, now I'm not talking like as a mystic, I'm talking as a scientist, to start with a mathematical model of consciousness and then show how what we call the physical world and physical objects, space-time and objects, and the brain arise from consciousness. So to motivate this, most of my colleagues would not be interested in that approach at all. They need some motivation. Why in the world, Hoffman, would you start with consciousness and then try to do it the physical world? The physical world, of course, is the fundamental reality. So for the last few years, I've been trying to come up with an argument for my colleagues to let them realize that their assumption that space-time and matter are fundamental is false. So here's the argument. Question is, do we see reality as it is? I open my eyes and I have a conscious experience. Here's my conscious experience in the cloud here. A conscious experience that I describe as a red tomato a meter away. I close my eyes and my conscious experience changes to a gray field. But most of us would believe that even though my experience is a gray field, in fact, in reality, there is still a red tomato a meter away. And I could verify that by having my friends say, is there still a tomato there? And they'd say, oh yeah, and so forth. Or I could reach out and touch it and so forth. I want to say that that assumption is deeply false. And that it's false in the same way that we've had other assumptions that we deeply believe but have turned out to be false. We used to think that the Earth is flat. Every bright person thought the Earth was flat because it looks that way. Until about the time of Pythagoras, and then Pythagoras and a few really bright Greeks figured out, well, no, the Earth is more like a sphere, around 500 BC or so. And then until about Copernicus, the received opinion was, okay, the Earth is like a sphere, but it's clearly the center of the universe and it doesn't move. And again, it's obvious to anybody that looks. It's not moving. Here it is. You can just look, it's not moving. And if the sun, moon, and stars are all obviously rising and setting, sunrise and sunset and all this stuff, clearly everything's going around us. So we're the center of the universe, and our perceptions, again, confirm that. Any fool could see it. And we were again wrong. So I want to say that our perceptions have misled us deeply in the past, and that they're misleading us about something even more fundamental. We assume that space and time and physical objects as we see them is reality as it is, and that's the assumption I'm going to question. Galileo, who was the one who built the telescope that he used to confirm Copernicus's conjecture that the Earth is not the center of the universe, Galileo began to suspect that our senses didn't just fool us about the geocentric universe, but also about other things. Galileo said, I think, that tastes, odors, colors, and so on reside in consciousness. Hence, if the living creature were removed, all these qualities would be annihilated. So he was saying, look, all the tastes, odors, colors that we experience, that's not part of the real objective world. Those are something that you create. That's you. Galileo did believe that physical objects, with their masses and their positions and their shapes, were part of objective reality. So so Galileo would have had a little problem with what I'm about to say. He wasn't there yet. So I'm going to take it one beyond Galileo, but Galileo was already halfway there. So if we look, I'll look a little bit about our perceptions of visual objects and visual perception. So here's the aspects of the brain that are involved in visual perception. All of the occipital lobe, the inferior temporal lobe, much of the parietal lobe is involved in vision. When you add it up, it's about a third of your brain's cortex. Billions of neurons, trillions of synapses have actions that are correlated with your conscious experiences in vision. The question is why? Now, for most of us, that's a bit of a surprise that so much brain activity is correlated with visual perception, because to the extent that we think about vision at all, we think of it as like just taking a picture, right? You just open your eyes, you take a picture of the real 3D world, the objects and colors and so forth that are already there, and taking a picture when we could do that even before there were computers. So why should we have all this computational power in the brain involved in vision? And it turns out there is an aspect of visual perception that's like a camera. The eye has a lens which focuses an image on the back of the eye, a place called the retina, where there's a piece of nervous tissue, the retina, that has about 130 million photoreceptors. And there's some sophisticated processing in the retina itself. You have hundreds of millions of interneurons which are doing sophisticated computations. The result coming out the optic nerve is about 1 million axons. So you have 130 million photoreceptors, you have data compression, 131 data compression after all this data processing coming out the back of the eye. Pretty impressive. So that's a pretty sophisticated camera. But it then goes, the optic nerve goes to your visual cortex and into all the brain areas I mentioned. And there now you have literally 20 to 30 billion neurons and trillions of synapses that are involved in processing the image. And the question is why? What's going on here? And the received opinion, and what I'm telling you now is standard fare in cognitive neuroscience. None of this is controversial at all. The idea is that we construct what we see. The reason we have all this cortical area involved in visual perception is because you're not just taking a picture of reality, you are actively constructing all the shapes, colors, motions that you see. And I'll just give you a couple quick examples just to give you a feel for that. I have some discs with parts cut out. If I just rotate them a little bit, you might all of a sudden see a three-dimensional cube popping out with glowing edges. Those edges are all hallucinated by your visual system. The glow is hallucinated by your visual system. The 3 dimensions are hallucinated by your visual system. And you can probably see 2 different cubes, one with corner B coming out in front, and then it can flip and you can see a different cube with corner A in front. How many people can see the cubes? Okay. These 2 tabletops, famous example by Roger Shepard, who was at Stanford. This long and narrow one, short and fat one, they're exactly the same dimensions. Your visual system, and if you want, you can come up after and you can measure it and so forth. They're exactly, I like to do this with acetate, transparencies, because I can't cheat. Everybody gets blown away when I show up with acetate. Here, you might see some blue bands with sharp edges that are glowing, moving across a field of black dots. All of that is you. There are no blue bands, there are no sharp edges, there's nothing moving. All I'm doing, and I won't, you can trust me or check it later on, I have a movie, I created this movie, frame by frame, all I'm doing, I'm changing colors of individual dots from black to blue or blue to black, that's all I'm doing. Nothing's moving. Your visual system sees how I'm changing just the colors of individual dots that aren't moving, and you create the whole story of the bands and their movement and the sharp edges, which aren't there. This is one you can check for yourself. The top and the bottom of this cube, same shade of gray or different. Look quite different, right? The top looks pretty dark, the bottom looks pretty light. If you close your left eye and put your index finger so that it goes over the bar between them, either the line between the top and the bottom, you'll see that they're exactly the same. So you're not seeing the true colors or true shades of gray. you're creating these. And I should say that we know with mathematical precision, our field, psychophysics, cognitive neuroscience, we're not just coming with these demonstrations, we have mathematical models that predict your conscious experiences. Consciousness is not some squishy stuff that you can't study. We can make mathematically precise theories which predict exactly the conscious experiences you will have in various, and that's going to be important in something I'll show you later. Here, the yellow and brown rectangles, same color or different. Okay, it's hard to imagine. I'm going to use Keynote to just move a bar up here, and you will see that they're exactly the same. You don't see the true colors in nature, so Galileo was right about that. You are constructing the colors that you see, and we have mathematical models for how you do that as well. These dots look flat. If I put them in motion, notice that you inflate a three-dimensional volume. You are creating a three-dimensional space. I'm going to argue that the three-dimensional space that you see right now is entirely inflated by you. And it doesn't exist except for you. And I've worked on this. I have mathematical equations that explain and predict exactly when you'll see a 3D shape and what 3D shape you'll see. So I can literally write down equations that explain precisely when your conscious experience will inflate a three-dimensional shape. So we have mathematical control in our understanding of how consciousness works. And it's because of this, because my field has been able, and artificial intelligence vision research, has been able to get mathematically precise understanding of how you create your conscious experiences. That's why we can create virtual reality. Without that mathematical knowledge, we could not do virtual reality. In virtual reality, we use the fact that we know exactly, with mathematical precision, how you create the three-dimensional world, the objects and shapes and colors that you see. We know precisely how you do it. That way we can now, once we know how the system works, we can play the system. So we've hacked into your own consciousness. We hacked into how you create your visual world, and we can now put you into any worlds that we want to with mathematical precision. So, what I've said so far is standard in the field. What my colleagues also say is not only that we construct what we see, they make a further and stronger claim. So it's one claim to say you construct everything that you see, the shapes, colors, and objects that you see. That's one claim. Notice that it's in fact a stronger claim to say that what you construct in fact matches objective reality. Right? That's a stronger claim. So the way it's put in my field is we reconstruct reality. The shapes of objects that we see in the normal case are reconstructions of the true shapes of real physical objects that would be there even if we didn't look. The colors that we see are reconstructions of the true colors and so forth. Notice that that's a stronger claim, and all I'm going to do today is propose that that claim is too strong. We should back off to just we construct. Everything that we perceive, we construct, and the stronger claim that my colleagues make is just too strong, and they were wrong, and I'll argue for that. So, but why do my colleagues say that we reconstruct reality? Well, the typical argument is an evolutionary argument, and we'll go into it in a minute. Here's a textbook that we use in my department for the graduate students, and in the introduction to the textbook, the author tells the students that evolutionarily speaking, vision is useful precisely because it's so accurate. The idea is that those of our ancestors who perceived or saw more accurately had a competitive advantage in the things that matter, feeding, fighting, fleeing, mating, over those who saw less accurately. And therefore, those who saw more accurately were more likely to survive and pass on their genes, which coded for the more accurate perceptions. So after thousands of generations of that, we can be confident that we're the offspring of those who saw more accurately, and so we see more accurately. And that sounds pretty good, right? Of course. I mean, what else could it be? So the idea is that accurate perceptions are fitter perceptions. And most of my colleagues believe this. And it turns out it's utterly false. It completely misunderstands evolution by natural selection. But before I tell you why, I'll just give you a couple humorous examples of where maybe our perceptions aren't really telling us the truth. There's a beetle in the outback of Australia. The jewel beetle, as you can see, it's dimpled, glossy, and brown. The females are flightless. The males fly, looking, of course, for eligible females, and when he finds one, he alights and mates. In the outback of Australia, there's another species, Homo sapiens, and the males of that species like full beer bottles. They're not interested in empties, and they throw the empties out in the outback. And it turns out that those bottles were dimpled, glossy, and just the right shade of brown to catch the fancy of these beetles. It turned out the male beetles would flock all over those bottles trying to mate, and that is what it looks like. He's excited. And the species almost went extinct. The real females were not of interest when these Amazons were available. And what that showed, so that's quite surprising. The males had successfully, for hundreds of thousands of years, used their senses to find and mate with females. You would think surely evolution had shaped them to know what a real female is. Clearly not. They had a little trick, a little hack. A female is anything dimpled, glossy, and brown. The bigger, the better. And so that was what they were looking for. And in their niche, that little trick was good enough. But just disturb the niche a little bit, throw a few beer bottles out there, and the species goes extinct. And in fact, 99.99% of all species that have been on the planet are extinct. So evolution does not shape us to see the truth. It gives you tricks and hacks for your niche. You might say, well, beetles, they have tiny brains. Surely not mammals. And I won't dwell on this, but you get the idea. Okay. So the question is, it's a nice, clean, technical question. Does natural selection favor seeing reality as it is? This is not a hand wave. This is a precise, mathematically precise question about natural selection. And it turns out that evolution by natural selection is now a mathematically precise theory. This is the equation of evolutionary game theory up here. And so we can use the replicator equation to study this question. And the key notion that's required is the notion of fitness. And so I'll just mention something about fitness. What is the fitness payoff that a T-bone steak offers to an organism? Well, if you're a lion and you're looking to eat, that T-bone steak could offer quite a bit of fitness payoff. If you're that same lion and you're looking to mate and you're full, the T-bone steak offers you no fitness payoffs whatsoever. And if you're a rabbit in any state, that T-bone steak doesn't offer you any fitness payoffs at all. So the notion of fitness, which is central in evolutionary theory, fitness depends on the state of the world, whatever the world might be, but also on the organism, lion versus rabbit, its state, like hungry versus sated, and the action, eating versus mating, fleeing, fighting, and so forth. So fitness functions, the fitness payoffs are complex functions, not just of objective reality, whatever objective reality might be, but also of the organism, its state, and the action. And think about evolution as like a video game. If you're playing a video game, you have to hunt for points as fast as you can, collect the points in the video game to try to get to the next level. If you do anything else, if you're dawdling around and just playing in the game, if you do anything except grab fitness points, you will die, you will not get to the next level. That's evolution. If you do anything except chase fitness payoffs in life, you will be outcompeted by organisms that do nothing but chase fitness payoffs. You don't go to the next level, but your offspring do. And so in evolution, it's like a video game in which if you succeed and collect enough fitness payoff points, your offspring then get to go to the next level of the game. That's a very useful analogy. And so, about 10 years ago, I began working with some graduate students and then later with mathematical colleagues. We ran simulations in which we have organisms that see reality as it is, organisms that see none of reality, and we have them compete in evolutionary games. And what my graduate students and I found in the simulations, about 1 million randomly chosen worlds that we looked at, organisms that saw reality as it is always went extinct when they competed with organisms of equal reality that were just chasing the fitness payoffs. So if you're only looking for fitness and you weren't looking for reality, even part of reality, just none of reality, you won. So that gave me confidence. There's something going on here. The standard view is wrong. And then I went and worked with Chetan Prakash, a mathematical friend of mine, colleague, and we proved a theorem. It's a theorem of evolution by natural selection. The probability is 0 that an organism that sees reality as it is will be more fit than an organism of equal complexity that sees none of reality and is just tuned to the fitness payoffs. There is no selection pressure to see the truth. In fact, the selection pressures are uniformly against seeing the truth, whatever the truth might be. So, you shall know the truth, and the truth shall set you free? No, it will make you extinct. If you see the truth, it will make you extinct from an evolutionary point of view. It's not just that I'm getting the shapes a little bit wrong, or the colors a little bit wrong, or the depths and so forth. It's that the very language of space and time, physical objects and shapes and colors, is the wrong language to describe objective reality. You could not frame a true description of the objective reality in that language. It's just the wrong language. That's what the theorem entails. So, how in the world could our perceptions be useful if they don't show us the truth? That seems like silly. The only way our perceptions could be useful is if they showed us the truth. And there's a metaphor that we can use that I couldn't have used just 40 years ago, but we now have it. And it's the desktop interface on your computer. Suppose that you're writing an email, and the icon for your email is blue, rectangular, in the right corner of your desktop. Does that mean that the email itself in your computer is blue, rectangular, and in the right corner of your computer? Of course not. Anybody who thought that completely misunderstands the point of the user interface, the desktop interface. It's not there to show you the truth, which in this metaphor would be the circuits, the voltages, magnetic fields, all that software. It's not there to show you that truth. In fact, it's there explicitly to hide the truth. If you had to toggle voltages to craft an email, your friends would never hear from you, right? The truth, knowing the truth, does not help you do what you need to do. It gets in the way. And that's what evolution has done for us. Three-dimensional space, as you perceive it right around you right now, is a three-dimensional desktop. And pretty soon, your laptop will actually have holographic three-dimensional desktops. This will be just everyday experience, probably in the next 10 years. And physical objects are just three-dimensional icons. And within the next 10 years, your desktop interface will also have a three-dimensional holographic interface with three-dimensional objects that you can manipulate around as your icons. So this will all make real sense then. None of this is here to show us the truth. Evolution did not give us space, time, and physical objects to show us the truth. This is here explicitly to hide the truth and to give us simple eye candy that lets us get the fitness payoffs we need to stay alive. We can control objective reality while we're utterly ignorant about its true nature. Just like on the interface, you can control the circuits even if you've never even heard of a circuit or believe in a circuit. You don't have to believe in the truth to make the truth do what you need it to do. So whatever the truth is, it's not space, time, and physical objects. And that means that our perception of physical causality, that I'm moving this paper, is a useful fiction, but it's just a fiction. No physical object has genuine causal powers. Clean prediction. No physical object has a definite value of any dynamical physical property, like position, momentum, and spin, when it's not observed. Clean prediction of this theory. If that was falsified, my whole theory would be false. But in fact, physics agrees with me, and we can talk about it. Obvious objection to what I'm saying. Hoffman, if you think that train coming down the tracks at 200 miles an hour is just an icon on your interface, why don't you step in front of it? And after you're dead and your theory with you, we'll know that that train was real, and it really can kill. And I wouldn't step in front of the train for the same reason I wouldn't carelessly drag my icon to the trash can. Not because I take the icon literally. The file is not literally blue and rectangular. But I do take the icon seriously. If I drag that icon to the trash, I could lose a lot of work. And that's what evolution has done. It's shaped us with icons that we have to take seriously. Evolution shaped them to keep us alive. If you don't take your icons seriously, you don't go to the next level of the game, or your offspring. You will die. So if you see a snake, don't grab it. If you see a cliff, don't step off. The icons are there to be taken quite seriously, to keep you alive. But it does not logically entail or even entitle you to take them literally. Our psychology has this interesting quirk where we think that because we have to take things seriously, therefore we must take them literally. That's just a logical error. But it's deep in our psychology. You might say, well, look, another objection is we all see the train, therefore the train must be real. Right? So it's an argument from consensus. We all agree, so therefore we must all be seeing the truth. But do you all agree that you're seeing a cube? Does the cube exist when you don't look? No. When you look, you create a cube, and when you look away, there is no cube. When you look here, you see a podium. When you look away, there is no podium. Physical objects are data structures that you create as you need them, and then you garbage collect them. You throw them away when you don't need them. So why do we have consensus? Because we're all members of the same species with a very similar interface. So we agree. But agreement in no way entails that we're seeing the same truths. It just means that we're constructing the same symbols in our interface. One last objection. You're not really saying anything new, Hoffman. This looks like, it feels like a hard, solid piece of metal there, a real train. But ever since Rutherford, the physicists have been telling us that what seems like hard, solid metal is really mostly empty space. There's a tiny nucleus with electrons whizzing around way far away, and it's mostly empty space. So yeah, perception doesn't match reality, and we've known that for a long time. There's nothing new here. That's very much like saying this. Yeah, I know that icon isn't the truth. But if I get out my magnifying glass and I look really closely, I can see little pixels, and that's the truth. Well, no, you're still on the desktop. Those are just pixels on the interface. You're not getting at the reality. And when the physicists say, look, it's not a solid piece of metal, it's mostly empty space, and there's, electrons and stuff whizzing around, they're still describing in space-time. That's the interface. They haven't got out of the interface. I'm saying something deeper. The electrons and neutrons and protons themselves they're not the objective reality, they're part of the interface. I'm saying something far more crazy than the physicists. I'll skip that. So, we naturally think of our senses as being a window on the truth. If our senses evolved and were shaped by natural selection, the probability of that is 0. Instead, our senses are give us a three-dimensional desktop. Space is your three-dimensional desktop, which you create on the fly. So, space and time is not the pre-existing stage on which the drama of life plays out, on which we're little bit players that happen 13.8 billion years later. It's just the opposite way around. We're not little bit players on the stage of space-time. we are the authors of space-time. You create it on the fly right now. It's a data structure that you create. And physical objects are just icons. In fact, I think of space-time as an error-correcting code for information about fitness, but that's another talk. But here's just a little thing about space-time that will help you maybe loosen up the grip of space-time on your imagination, because it's really hard for us to think of space-time as anything but the pre-existing stage in which the drama of life plays out. Suppose I have a volume the size of a volleyball, and I ask you, how much information can you put in that volleyball, into that volume? Well, you might say, well, with today's technology, I could stick 5 terabyte hard drive in there, and next year maybe 10 terabytes. And the question is there some ultimate limit? Is there some principled limit about how much information you could store into that volume of space? And it turns out the answer is yes, and no less than Stephen Hawking was the one who figured it out. Hawking showed that the amount of information that you can store into a region of space does not depend at all on the volume of that region. If you let that sink in, that will destroy everything that you believe about space-time. It cannot, volumes of space-time do not hold information. What he showed was the amount of information is proportional to the surface area bounding the region. This is called the holographic principle. It's only been known since Hawking and others worked on this a few decades ago. Physicists now view it as a fundamental guiding principle in physics, and they don't know what it means yet. But it's a very, very powerful principle. This does mean, for example, that if you have a big volume and you, say, find 6 spheres that you can just pack inside of it, and you ask, if you're a computer engineer and you're trying to build a memory device, and you ask, should I try to use the big sphere or the 6 smaller spheres to hold information? Which will hold more information? If you do the math, you'll see that the 6 smaller spheres have 3% more surface area than the bigger sphere. Only half the volume, but the volume's irrelevant. So you should use the 6 smaller spheres. And if that's blowing your mind about how space-time works, that's my goal. Space-time works utterly differently than anything you've ever imagined. And I'm not the only one that's, so it's one thing for cognitive scientists to be saying this about space-time, but space-time, of course, is the proper turf of the physicists. So we should defer. What are the physicists saying? Nima Arkani-Hamed, who's at the Institute for Advanced Study at Princeton, if you Google the phrase, space-time is doomed, and I highly recommend it, he has some wonderful videos, some of them for a broad audience. You don't have to be a physicist. And he says this, space-time is doomed. There is no such thing as space-time, fundamentally, in the actual underlying description of the laws of physics. That's very startling, indeed, because what physics is supposed to be about is describing things as they happen in space and time. So if there's no space-time, it's not clear what physics is about. And that's the state of play. Physics, since Newton, has been about what happens in space-time. And space-time has had a good run. It's been a very, very powerful concept. The idea that space-time is fundamental, physical objects really exist when they're not perceived, and they have causal powers, that has been a wonderful framework. It's done lots of good work. But that horse is now tired, and it's time to get a new horse. And the physicists don't know what the new horse is going to be. But someone like Nima Arkani-Hamed is not worried. For the young Turks, this is fabulous. This is good news. This is their chance to make new discoveries. And so it's going to be exciting to see what they come up with. It's hard for us to imagine that physical objects don't exist when they're not perceived. So I want to give you just a couple examples that might help you with that. Synesthesia. 4% of us have perceptions that differ from the rest. In one, there was a guy named Michael Watson. Everything that he tasted on his tongue, he also felt as a 3-dimensional object in space that he could touch with his hands. In the case of Angostura bitters, he felt a basket of ivy. He could feel the leaves, he could feel the texture of the leaves, the temperature, the whole bit. And he used it for cooking. He was a really excellent cook because he had this new way of perceiving tastes. As long as he tasted the Angostura bitters, he would create this object. As soon as the taste wore off, he got rid of the object. The object disappeared. So a three-dimensional object with textures and shapes and temperatures was a data structure that Michael Watson created on the fly as needed for cooking and tasting, and then threw them away when he didn't need them. So here we have an example of a man who created three-dimensional objects not as perceptions of objective reality, but as simple data structures to do things like cooking. When he tasted mint, he always felt a tall, cold, smooth column of glass. And as soon as the mint wore off, he garbage collected that data structure. And I'm saying that this podium is just another data structure. You create it when you look, you garbage collect it when you don't need it. We create objects on the fly and throw them away when we don't need them. Carol Steen, I've had the privilege of communicating with by email quite a bit. Whenever she hears any sounds, she creates three-dimensional objects that have specific textures and colors and shapes and motions. When she hears the sound Saito, this is the sculpture of what she perceives, but she is very careful to say this misses the whole dynamical component of her perception. And so she sees, so this she literally sees this three-dimensional object as though it were right there. It's vivid for her. And every sound has a three-dimensional object with colors, textures, and shapes that's changing in real time. And when the sound disappears, so does the object. So objects are a data structure that Carol Steen uses as another modality of representing sounds. She uses them, she creates them when she needs them, she throws them away. Now, I'm hoping this will help you to realize that there are humans that we know create three-dimensional objects and throw them away as and I'm saying you do that too, all the time. So, what does this mean? When I open my eyes, when I have an experience that I describe as a red tomato a meter away, I am interacting with some kind of reality. So I'm not proposing solipsism. There is an objective reality, but that reality, according to evolution by natural selection, is utterly unlike anything that we perceive. So I don't know I won't say what that reality is, but I'm just putting up digital rain to say it's utterly unlike anything that you perceive. So this is digital rain as you saw in the Matrix. When you open your eyes and you see an object that you describe or have an experience that you describe as a lion, again, you're interacting with reality, but it's unlike a lion. And here's the kicker now for the hard problem of consciousness. As a neuroscientist, if I look inside a skull and I see brains, and I whip out a microscope and I see neurons, I am interacting with an objective reality. But that objective reality is not neurons, it's not the brain. And it's utterly unlike neurons and the brain. Neurons do not exist when they're not perceived. The brain has no causal powers. Neurons have no causal powers. They are data structures that we create on the fly as needed and garbage collect them when we don't need them. So the very idea that neural activity causes our conscious experiences is doomed from the get-go. It assumes that neurons exist and have causal powers, and they don't. And that's why we have been struggling with this problem since at least 1700, when Leibniz clearly enunciated the problem. And my colleagues have made no progress on it. We've assumed that neurons create conscious experiences somehow, and neurons create nothing. In fact, neurons cause none of my behaviors and none of my experiences. Now, it's a useful fiction in modern neuroscience to talk about neural activity having causal powers. All in my casual conversations with other neuroscientists, I'll talk about how activity in area V1 projects to area V2, and then there's back projections from V2 to V1. And for everyday neuroscience, that's harmless. It's useful. It's a very useful assumption to talk as though neural activity has causal powers. It's perfectly harmless and in fact useful. So I have no objection to doing that. It's only when we try to look under the hood. How does neuroscience, neural activity, relate to conscious experience, that then the assumption that neurons have causal powers comes back to bite us. So, for example, if I'm playing a video game, like Grand Theft Auto, and I talk with friends about how you can use the steering wheel and all this stuff to do stuff as though the steering wheel in the video game really has causal powers, it's perfectly harmless. Within the video game, it's perfectly harmless to talk about that steering wheel. When you turn it to the left, the car goes this way, and so you put on, perfectly harmless. But if you're a software engineer, and you're trying to build a video game, that assumption is no longer harmless. If you think the steering wheel really has causal powers, good luck. You're not going to be able to make a video game. That's where we are. We've gotten to the point in neuroscience where we have to look under the hood, and the assumption that physical objects have causal powers is no longer harmless. So space-time is doomed. You make space-time. Physical objects are doomed. And neural causality is doomed. That's why the hard problem has been so hard. By the way, if you want to read more about this, a little plug. I have a book where I go through this in much more detail called The Case Against Reality. It's coming out in August. So, little ad. So, going back now to the question of conscience, how much time do I have now?
Oh, at least an hour, and then afterwards there's space for discussion.
So I have more time to... Oh, okay, good.
It's not the lead.
Yeah, the time, that's right, yeah. Actually, it's very, very interesting. Some quantum physicists have just published an experiment in which they can actually make time go backwards. So that's really, really interesting. So, going back to the hard problem of consciousness, all of my colleagues have assumed physicalism, that neural activity causes conscious experiences. So we start with the brain, we assume the brain exists and has causal powers, and somehow consciousness arises from it. That hasn't worked, and what I've done is to show that a deeply held theory by my colleagues, evolution by natural selection, is in flat contradiction to their physicalist assumption. And I should just point out, you might say, well, look, evolution by natural selection assumes physicalism. DNA exists when it's not perceived. Organisms exist when they're not perceived. So what have I done here? Have I used the theory of evolution by natural selection to disprove the theory of evolution by natural selection and effectively shot myself in the foot? A logical contradiction. Is that what I've done? The answer is no. What I've done is I've used what's called universal Darwinism. Evolution by natural selection, at the heart of it, has an algorithmic core called universal Darwinism. Dan Dennett and Richard Dawkins talk a lot about this evolutionary core and point out that the basic principles of evolution don't just apply to biology, they can apply to ideas. They call them memes. Why do certain songs go throughout the whole community and we all know them, and other songs, any song that I've written, you probably have never heard of. So why is that? Well, there's again this competition. There's a natural selection process that goes also with scientific theories. I mean, scientific theories also compete. And so this is called universal Darwinism. The basic algorithm is variation, selection, retention. And that algorithmic core makes no ontological assumptions at all. And that's the key point. This is an abstract algorithm that can apply in any world, not just a physical world. And what I've shown is not that evolution by natural selection is self-refuting, but rather that the algorithmic core of evolution by natural selection refutes the physicalist accoutrements that my colleagues have put. That part is wrong. The basic idea of evolution still holds. So it's not a self-refuting thing. One other question you might raise is, well, does my argument not only show that our perceptions of space-time and objects is false, what about our perception of math and logic? Right? If I use evolution and show that math and logic are also false, then I've shot myself in the foot again. I've used math and logic to show that math and logic don't work, So I've got myself in another hole. So have I done that? And the answer is no. The argument that I give, and the theorem that Chaitanya and I proved, does not hold against math and logic for the following reason. We do have to reason about fitness payoffs. Someone who does not, in practice and perhaps in theory, understand that 2 bites of an apple give you roughly twice the fitness payoff of 1 bite of an apple will be less fit. So there are selection pressures for modest ability in mathematics. And also because we're a species that has social contracts. If I do something for you, I'm expecting you to do something for me. I'll need to be able to check later on that the balance sheet is roughly the same. For social beings like us, we need to have some elementary logical abilities to make sure that if I did this for you, then you later on did. So we have this if-then logic. So again, we need the math and logic not for the objective reality, but for dealing with fitness payoffs. This is not an argument that we're going to be geniuses at math and logic, just that we have satisficing abilities. So whereas natural selection pressures are uniformly against true perceptions of like space-time and objects, it's uniformly against that. It's not, the selection pressures are not uniformly against math and logical abilities. There are modest selection pressures. There are not selection pressures for us to be geniuses. Every once in a while, the genes align and you get a von Neumann or David Hilbert or something like that. People that we can only, I wish I had that too. But most of us don't have that. So it's not self-refuting. So physicalism is false. And physicalism, which led to all this magic whenever you try to get consciousness emerging, the reason why there was always magic is that physical objects have no causal power. So right in the point where physical stuff is supposed to cause consciousness, that's when you get hit, and it's only magic. So I'm proposing what I will call conscious realism. Instead of saying that space-time and physical objects are fundamental, let's say that consciousness is fundamental. As a scientist, then, I need to have a mathematical theory of consciousness on its own terms. And what's interesting is we haven't done that before. When you look at the theories of consciousness that my colleagues have been working on, what they really are theories about physical systems that might somehow give rise to consciousness. So they talk about physical systems and their properties that would then give rise to consciousness. We have to do something entirely different. We have to step back and say, look, physical stuff, space-time and physical objects, that's just Homo sapiens user interface symbols. Those are the wrong symbols to even try to frame a theory of consciousness. We can't start there. So we have to start consciousness on its own terms. What do we want to put as our theory of consciousness on its own terms, not as something that arises from physical stuff? So this is quite a bit of a challenge. And I'll just say just a little bit about what we want to do in science here. As scientists, we want to create theories that have as few assumptions as possible. No scientific theory explains everything. Every scientific theory says, grant me this handful of assumptions. And if you grant me these assumptions, we can call them miracles, because from the point of view of the theory, they're completely unexplained. And that's what I mean by a miracle. These are things that the theory says, I'm taking these things for granted. I can't explain them. And I use the word miracle. It's a bit of a jar. Most scientists wouldn't like that, but it gives you the flavor. These are things the theory cannot explain. If you grant me that, so if I'm a physicalist, grant me space-time and matter, or quantum fields. If you grant me that, then I can explain how chemistry and biology evolve, and hopefully psychology, and then consciousness. And it's turned out that it got pretty far, but not far enough. So we want the smallest number of assumptions that we can get away with. And so that's tough. What are the minimal assumptions that we want to make? In the case of consciousness, if you think about the kinds of things you want a theory of consciousness to explain, it's quite large. The self, attention, memory, problem solving. But there's tons and tons of things that you'd want it to do. Out of all the things we want a theory of consciousness to do, what shall we pick as the elementary? So I'm going to propose a very simple idea. I'm going to propose that there is a world. For the moment, I won't say what the world is. That world affects our experiences. And by experience, I mean simple things like the taste of chocolate, the smell of garlic, so forth. So a conscious agent, I'm going to define this thing I call a conscious agent. It has a set of experiences. And based on those experiences, it can take action. So it has a set of actions. And those actions, it can then act on the world. And the first step is to, mathematicians get rid of words and start putting symbols. So there's a world. The agent has a set of experiences. Might be only two experiences. It could be a very simple conscious agent that has only two experiences. Like it sees red and green, that's all. Smells chocolate and vanilla, that's all. Based on its experiences, it chooses an action. So this arrow is going to be, given that I have an experience, what action do I choose? Okay. And then once I've chosen an action, my action will change the state of the world. So any action I take will change probabilistically the state of the world. When the world changes its state, it will probabilistically change my experiences. And so I'll just these arrows that are the things that happen, I'll just model them. There's a perception arrow, a decision arrow, and an action arrow. And then finally, each time the agent gets an experience, it can increment a counter. So the n is the number of experiences that that agent has had. That's the whole thing. A conscious agent has a perception map which changes its experiences, a decision map which chooses its actions, an action map which acts on the world, and it counts. Notice how drop-dead simple that is. There is no self. There's no self-consciousness involved in this. There's no memory. There's no intelligence. There's no problem solving. It's literally as drop-dead simple as I could think about. A conscious agent has experiences, makes decisions, and takes actions. I can prove, quite simply, that this formalism, because these arrows with the actions are so-called Markovian kernels, and that's a technical thing. They're Markovian kernels. I can prove that my formalism is computationally universal. Anything that you can compute with a neural network or your laptop, you can compute with conscious agents. So, even though I've started with this unbelievably simple starting point, there's only experiences, decisions, and actions. It's a theorem that I can build models of learning, attention, problem solving, intelligence, the whole bit. I can do it all. And the reason I didn't put those in to begin with, I didn't put in a self, I didn't put in memory and so forth, is because if I put them in at the front, they would be miracles. Now, there's stories that I can build. There are scientific theories that I can build. So the miracles I'm proposing, so here are my miracles. In the universe, there are things that are conscious experiences. That's a miracle. And there's something that you might call free will. When I have an experience and I choose an action, probabilistically, those probabilities are not about objective chance. Those are about an agent making a choice. So there is a theory of free will that falls out of this, and then there are actions that you can take. Those are my miracles. I have 3 miracles. The idea is to start with only those 3 miracles and then build up a theory of everything, including space-time and physical objects. So a conscious agent, mathematically, is this 7-tuple. WXG, PDAN. This is for free, you don't need this, but WXG are probability spaces. They're actually measurable spaces. PDA are Markovian kernels, and N is actually not an integer, it's a totally ordered set. So it's all mathematical. Mathematicians can now, and my colleagues can actually attack me because it's absolutely precise. And by the way, as I mentioned yesterday, why am I being precise like this? Is it a mathematical fetish? Is it some weird thing? It's not that. The point is to be precise so that you're not wasting people's time. Be absolutely precise so that people can see precisely what you're saying and try precisely to show you where you're wrong. It's all about making progress. That's the point of science, is to be precise. So we've talked about consciousness for a long time. It's now time for science to get serious about it and be absolutely precise so that we can start to say theorems and proofs about our models of consciousness. So, the conscious agent thesis. Here's the bold proposal. Every conscious entity and every activity of consciousness can be modeled by conscious agents. And again, I don't know if it's true, but the point is to be precise and bold. I'm proposing that the theory of consciousness, the conscious agents I just wrote down, can do it all. There's nothing about consciousness that cannot be explained by this. And we'll see. Right? We'll see. And then I have one other hypothesis I call the conscious realism hypothesis. And that is, what is that world W? Right? I put W as just some world out there. So, what is W? And here is the big move. The world W is just other conscious agents. The universe, the fundamental reality, is a vast social network of conscious agents interacting. That's the proposal. So instead of the universe, the fundamental reality being just space-time and physical objects and quantum fields and so forth, I'm throwing that whole thing away and saying, I have another monism. The monism is consciousness all the way down. So the idea is this. I have a conscious agent over here. Here's conscious agent number 1, right? I've put little subscripts 1 with its world W. Here's conscious agent number 2 with its world W. And what I'm going to do is I'm going to take this agent and plug him into the world of that agent, right? So I'm going to replace the W with another conscious agent. So if I do that, you're actually seeing the process. There I go. Here's agent number 1. Its actions are affecting the experiences of agent number 2, and the actions of agent 2 affect the experiences of agent number 1. And you get a circuit. And you can do more than 2 agents. You can do 3, 4, infinity. So the idea is, here's 3. So agent. So this is just one kind of circuit that you could have. Here's agent 1 talking to agent 2, talking to agent 3. They could have a cyclic kind of talking. Or they could be, here's agent 1 talking to agent 2 and to agent 3. There's different kinds of topologies of this network that you can have. You could have this. Here's agent 1 talking to agent 2, agent 3, agent 4. And you can go off to an infinite network. So the idea is, reality is this vast, infinitely complicated social network. Think of it like the Twitterverse, right? There's millions of Twitter users out there. You're following and being followed. This guy is following him, right? This guy's tweeting, this guy's listening. This guy's tweeting, that guy's listening. So think of this. So the Twitterverse is a good model of what I'm talking about. It's this vast, infinite social network of conscious agents that are sending experiences and receiving experiences. And suppose you're trying to understand the Twitterverse. There are millions of Twitter users and billions of tweets and all sorts of stuff trending. And suppose you're a big data engineer. You're trying to understand this. You're trying to understand what's happening, and what's happening in Ojai, what's happening in Los Angeles. It's overwhelming, right? Billions of tweets. How are you going to deal with that? What you will do, and what's in fact being done, is you build visualization tools. That's what this is. Space-time and physical objects are nothing but a visualization tool that you're using to navigate this vast social network of conscious agents. We mistook our visualization tool for the reality. Simple mistake. But there were no selection pressures for us to understand this. A creature who takes its perceptions seriously and literally has just the same survival capability of one who takes it seriously and not literally. There were no selection pressures for us to recognize that this is just a visualization tool, but that's all it is. So physicalism is the simple mistake of mistaking our visualization tool for the reality that it was there to visualize. Simple mistake. And that's why the hard problem has been so hard. So I was surprised. I wrote down the mathematics, and one reason why we write down mathematics is that the mathematics is smarter than you. Once you write down a mathematical theory in the sciences, the person who writes it down then becomes a student of their own theory. That's one reason why we write down mathematics, because the mathematics has all sorts of implications that most of us are not bright enough to figure out, even if we're the one that wrote it down. So as I was playing with the mathematics, and I started to look at interactions of conscious agents. What happens when two of them start to interact? It's sort of fun. It's fun to start building these circuits. Look, you can actually program, and my students, I have a postdoc who's actually building networks of conscious agents as we speak. We're simulating these networks, looking at their properties and so forth. As I wrote it down and started to look at it, I realized that mathematics said this: when you have two agents interacting, that pair of agents, when you write it down formally, it satisfies the definition of a conscious agent. And so I have to take the mathematics seriously. The mathematics is saying, when two agents interact, there is a new agent. So when two agents interact, a new agent is born. And so there is a smallest agent that literally has only two perceptions and two actions. I call it a one-bit agent. You only need one bit to describe its perceptions, one bit to describe its actions. When two of these one-bit agents interact, you get a two-bit agent. When two of them interact, you get a 4-bit agent, 8-bit, all the way up to infinity. Notice that when we start talking about infinite conscious agents, now we're clearly in the domain of spirituality. But now I have complete mathematical control. I can define, and again I'm probably wrong, but I can precisely define what I might mean by the word God as an infinite conscious agent. I can prove theorems about infinite conscious agents and their relationship with finite conscious agents. Because if there is an infinite conscious agent, I'm actually part of it. According to this mathematics, I and other agents are combining together to form an infinite conscious agent. So now there's the nice technical question. So I'm not separate from the infinite conscious agent. How much can a finite agent that's part of what I call the instantiation of a bigger agent, how much can that lower level agent know about the higher level agent? I honestly don't know. That's an open question. I'm looking to the math. So I'm going to be actually proving theorems about how much. In other words, these are going to be theorems about spirituality. How much can a finite consciousness know about higher consciousnesses? It's now a matter of theorem and proof. Again, not that I'm right, but at least I'm precise, so we can figure out precisely where I'm wrong. We can turn spirituality into a mathematically precise science. There's going to be a science of spirituality that I hope brings the best of both together. So two agents interacting together form a single conscious agent. You can have models of introspection, an agent that looks at itself, so you can actually build introspective models. And then I'll close with just one of the steps forward that I'm really interested in. I now need to solve the hard problem of consciousness going the other way. Instead of saying I start with space-time and matter and neurons and somehow booting up consciousness, I have to start with this vast social network of conscious agents and a particular visualization scheme that gives me back all of modern physics, space-time, general relativity, quantum field theory, and so forth. And I'm working with my colleagues, we're using tools of geometric algebra to actually show that we can get back relativistic quantum conformal, supersymmetric conformal field theory out as a visualization tool. So what the physicists have been doing has been very, very carefully studying the visualization tool that we're using to, understand this network of conscious agents. And so what I wanted to do is be able to show how I can get back exactly the tool that physics uses. But then, this also extends to what you might call a multiverse. Our interface of space, time, and matter is just one of infinitely many different interfaces that are out there. So I'll first try to show that we can get this one, but then we can explore others that are possible. And I'll close with an interesting application. One that I plan to be talking about this fall at a conference called Science and Non-Duality in San Jose. It's the question of artificial intelligence. AIs are here, and artificial narrow intelligence is now mature. Artificial narrow intelligences can beat us at any specific thing that we program to do. Playing Go, talking, all these things. There are these artificial narrow intelligences that use deep learning that are just trouncing us everywhere we turn. That's fairly mature, just in the last 10 years that's happened. Artificial general intelligence is still a long way off. We don't have the mathematical tools yet to build an artificial general intelligence. But Google is working on it, and they're very interested in techniques for doing that. I was just talking with them about that. But there's a deep question: could AIs not just be intelligent, but could they be conscious? And that's going to be more than just an academic question very, very soon. When you have a home robot that knows more than you, that can beat you at any game, that is smarter than you in everything, that can write poetry, that can create music, that can write novels, it's going to be almost strange to not think of it as being conscious. It's going to be very, very strange for it. And so the question is, will they really be conscious or not? This question has been addressed until now entirely in a physicalist framework. The question is, under what circumstances do physical systems, circuits made out of silicon and so forth, get complicated enough that somehow the magic of consciousness appears? And we have no idea how that magic can happen. That's the hard problem of consciousness. So most of my colleagues say, yes, AIs will eventually be conscious, but they have no theory about how that could be. What about from my point of view? I have to completely reframe the question. It's not when do unconscious circuits, which are the fundamental realities, somehow give rise to consciousness. That whole framework is gone. The framework is very different. What exists is a vast network of conscious agents. Space-time and matter is just a visualization tool. And to see that, just imagine looking at your own face in the mirror. When you look at your face in the mirror, you see skin, hair, and eyes. But what you know firsthand that you're not seeing is the vast realm of your conscious experiences. Your fears, your desires, your aspirations, your love of music, all the colors and shapes that you're experiencing. That whole infinite realm of your, or very large realm of your conscious experiences is not visible on this little interface. Our interface, when I look at your face, I have a little portal into your realm of consciousness. Very fallible. If I see a smile on your face, I infer that you have the experience of happiness. But notice that a smile does not resemble happiness. There's no resemblance. That's just an interface symbol. And we use the smile as an inference about the realm of consciousness. So we have firsthand knowledge that our interface, space-time interface, gives us portals into other conscious agents. Your body is my symbol. The body that I see is my symbol, right? I'm creating the body. Right. I don't see you. I don't see your consciousness. I see a body, which is an icon that I've created. But that icon is a portal into your consciousness. You don't see my consciousness. You see a body that you're creating, and it gives you a portal into my consciousness. We know firsthand that the portal is real and also very narrow. You can live with a person all of your life. You can be married to them and discover new stuff all the time. It's a very narrow portal. When I look at my cat, I have a portal into the cat's consciousness, but it's even worse than my portal into humans. When I look at an ant, my portal is almost non-existent. And when I get to something like a podium, I've given up. I'm not saying that the podium is conscious. I'm saying that podium is a symbol that I'm using as I interact with the realm of conscious agents. But because I'm a finite agent, and I have finite resources, at some point I have to give up. That was the whole point of the interface, was it's too much. So, of course, there are going to be parts of my interface that give me no insight into the consciousnesses that I'm interacting with. That's part of the reason for the interface. We've mistaken the limit of our interface for an insight into the nature of reality. That's the problem of physicalism. Our interface necessarily is limited. That's what it's for. It necessarily is not going to show us the nature of consciousness that we're interacting with. Necessarily. And we've mistaken that necessary limit as an insight into the nature of reality, that reality is not conscious. So, now the question of AI consciousness. The question is this, completely reframed question. It's not, when do real physical circuits somehow give rise to the magic of consciousness? Rather, it's this. Is it possible for us to rejig our interface to open a new portal into this pre-existing realm of conscious agents? We're not creating the consciousness. The consciousness is already there. See, that's different. The AI traditional thing is, there is no consciousness out there. It's, will we create consciousness by having the silicon be complicated enough? This is different. We know we have portals. I have a portal into your consciousness. So we know that it's possible to have portals into this realm of conscious agents. We know that that's possible. The question, the technical question is our interface such that we have the technical ability to rejig our interface and open new portals into the realm of conscious agents? And if so, we might actually be walking into realms of conscious agents that are utterly alien to us, that have experiences that we can't even imagine. I mean, if I ask you, imagine a specific color experience that you've never had before. Does anything happen? Right. I try to imagine a specific color experience you've never had before. Right? Smoke comes out of my ears and nothing happens. Our senses are our window, but they're also a prison. We can't even think or imagine it's unbelievable. Not even one silly conscious experience that we've never had before. We can't even imagine it. And yet we know theoretically, right, that, imagine I'm a colorblind guy. I have poor red-green perception because I'm missing the green cones. And there are people that are trichromats that can see them. That poor guy cannot imagine any one of the specific color experiences that the rest of us color normals have. So we're all having these color experiences. That poor guy cannot even imagine them. He's in a prison. Can't even, and there are pigeons that have 4 color receptors. The mantis shrimp has at least 10. We're not at the peak of the color world. We're by a long shot. Presumably the mantis shrimp might have 10 dimensions of color experience or more. We can't imagine what it's like. So the realm of conscious agents out there are infinitely many conscious experiences that we are unable to concretely imagine. We can still do science because I don't have to concretely imagine. I can just say they satisfy these rules. And I can do science. So I don't have to be able to imagine, just like I can use mathematics, and Einstein talked about a 4-dimensional space. Can you imagine a 4-dimensional space? I can't. No, Einstein couldn't. But he could write down the math, we can still do the math. So we can do the same thing with consciousness. So the technical question here, and I'll stop with this, can we rejig our interface to open up new portals into the pre-existing realm of conscious agents? And for what it's worth, I think the answer is yes. And with that, I'll stop.
Thank you.
Yeah.